So now we have all the pieces in hand that we need in order to expand the direct and indirect parts of the disturbing functions to arbitrary order in the eccentricity and inclination. Let's consider a second order expansion. This matches very closely the result that is given in section 6.5 of Murray and Dermot, and so you can refer to that for additional details. We will define the ratio of the semi-major axis, that A2 over A3 term that keeps popping up, as quantity delta. For notational shorthand, we define the operator d to the n as the nth derivative in this ratio delta. We will define s sub I as the sine of half of the inclination of body I. And finally, we will be using the mean longitudes of the bodies, these lambda sub I terms, which are defined as the mean anomalies of the bodies plus their longitudes of periapsis. Again, remember, this is capital omega plus lowercase omega, the sum of the argument of periapsis and the longitude of the ascending node. We plug all of this into that quadruply nested infinite series that we wrote down for the direct part of the disturbing function. And remember, we are interested in going to second order in eccentricity and inclination, with the implication being that we are describing orbits with low eccentricity and low inclination, which is true for example, the orbits of the major bodies of the solar system. They are all relatively near the ecliptic, and so if we're using ecliptic coordinates, they all have small inclinations, and they are all nearly circular, and so they all have small eccentricities. So this is what happens when you evaluate all the internal summations inside of these outermost infinite summation over the J index and only keep terms up to second order in eccentricities and these S values. We do the same thing for the indirect terms, and we get this expression for the external perturber part and this expression for the internal perturber part. Remember, this goes into the R2 disturbing function, and this goes into the R3 disturbing function under the assumption that body 3's orbit lies outside of body 2's orbit. Because RE and RI are only expansions in alpha, they automatically contain a finite number of terms when we're expanding to second order in eccentricity and inclination. The direct part, R sub D, unfortunately has an infinite number of terms. And in particular, it will have an infinite number of cosine terms of various arguments, as you can see here, here, and so on and so forth. However, only some of these cosine terms are actually going to be significant for a given problem. We've already seen that we can average perturbations, and we can do so in this case as well to give ourselves a strictly finite set of terms that we need to be interested in for a particular averaging system. In Murray and Dermot, section 6.7 to 6.10, there are detailed algorithms for using tabulated expansions of this form. And this is an approach that was frequently taken in order to try to get at some long-term behavior of n-body systems without having to do numerical integration. As we've seen from our discussion of numerical integration techniques, at this point, it's not clear whether this is actually giving us any kind of superior information. So instead, what we want to focus on is the physical significance of these terms and to understand what they can teach us about long-term n-body system behavior. A key thing to note here is that every argument of every cosine function here is a linear combination of the mean longitudes, longitudes of the ascending node, and longitudes of periapsis of the two bodies. That is, every one of these is composed of some linear combination of lambda 2, lambda 3, var pi 2, var pi 3, and capital omega 2, capital omega 3. In an unperturbed system, all of these angles are constant except for lambda, which you recall is a function of this constant var pi plus the linearly changing mean anomaly. And so what that means is that any of these cosine arguments that contain lambdas will evolve rapidly. And any of these terms that do not contain lambdas, under the assumptions that the perturbations are small in this system, will vary very slowly. We've already seen this type of behavior. The slowly varying terms are going to be giving us our secular perturbations. To help us classify the various different flavors of these arguments to the various cosine terms, we will define a general argument of the form phi is defined as coefficient constant C1 times lambda 3 plus constant C2 times lambda 2 plus C3 times var pi 3 plus C4 times var pi 2 plus C5 times capital omega 3 plus C6 times capital omega 2. We will define a mean longitude at epoch such that mean longitude can be written as mean motion times time plus this mean longitude at epoch, epsilon, which represents the mean longitude at the time of periapse passage. Because remember, lambda is equal to m plus var pi, which is the same as n times t minus t of periapse passage plus var pi. So if we express lambda in this fashion, taking out the nt and grouping everything else into this epsilon will be var pi minus n times the time of periapse passage. With this definition, we can therefore write C1 lambda 3 plus C2 lambda 2 is equal to C1 n3 plus C2 n2 times time plus C1 epsilon 3 plus C2 epsilon 2. This is the fast part of the variation. And these two terms, C1 epsilon 3 and C2 epsilon 2, are approximately constant, as we expect the variation in the epsilons to be very, very small. We can also consider the case where A2, the oscillating semi-major axis of the second body, is approximately C2 over C1, absolute value, to the 2/3 power, times the oscillating semi-major axis of body A3. From Kepler's third law, we know that this represents an integer ratio between orbital periods. In fact, if this expression is exactly equal, then we will have an exact integer ratio of orbital periods. This condition leads to C1n3 plus C2n2 being approximately 0. That is, this leading argument being approximately 0. When this is true, then phi, our generalized argument, will have a period that is longer than either of the two orbital periods. And this leads to resonant terms. So we now have at least two possible flavors of these cosine terms. We have secular terms that are independent of these lambda values, which will vary slowly over the course of many orbital periods and lead to systematic change in the orbits. And then we have resonant terms that again get rid of these fast variations and can lead to long-term variations. Secular terms are global, but resonant terms depend very strongly on the current semi-major axes of the objects, and so are local, temporally local in the sense that you can evolve into resonance if you get into anywhere near these kinds of relationships between the evolving semi-major axes. Everything else, everything that isn't resonant or secular, is short period, and therefore can essentially be ignored. Everything that acts on a time scale of less than an orbital period is going to damp out, is going to average out. And just as we showed in our analyses on orbits around non-spherical central bodies, the short period variations do not impact our long-term evolution of the orbital elements. So the only thing that we care about in this infinite set of coefficients are secular and resonant terms. And this is the fundamental mechanism by which we reduce this infinite summation into a strictly finite one. In order to utilize these expanded disturbing functions, we are going to introduce a slight modification to our Lagrange's planetary equations. You will recall that in our original derivation, we found differential forms for the Keplerian elements. So the semi-major axis, eccentricity, inclination, longitude of the ascending node, argument of periapsis, and mean anomaly, or mean anomaly at epoch. In this case, we are using the mean longitude and the longitude of periapsis and have defined the mean longitude at epoch. And so we can modify those original differential expressions to now be derivatives in time of these elements, epsilon dot and var pi dot. You can do this either by substituting in the algebraic mappings between these terms and the original terms in the original differential expressions, and then crunching out the algebra and the derivatives, Or you could go all the way back to our original derivation via the Delaunay elements and take that last final step where we set up the Jacobian of the transformation to be the Delaunay elements mapped to this element set instead of the Keplerian orbital elements. Regardless of which approach you take, you will get this same set of expressions. An important thing to note here is that epsilon dot is a function of the partial of our perturbing potential, the disturbing function, in the semi-major axis. And so if we are carrying out a partial derivative on any term that includes the semi-major axis, for example, all of the Laplace coefficients, then we will get terms in time. And it's a little annoying having time as an explicit factor in these differential expressions. So there's an alternate approach that we can take. We can define epsilon dot prime as epsilon dot plus Tn dot. That is the original variation in the mean longitude at epoch plus time times the derivative of the mean motion. Since lambda is equal to nt plus epsilon, we can write lambda dot is equal to n plus epsilon dot prime. And that means lambda is the integral of the mean motion in time plus epsilon prime. Remember that we can also write the second derivative of the integral of n in time is -3/2 n over a times a dot. This is coming to us straight from Kepler's laws. And that means that this second derivative is equivalently equal to -3 over a squared times the partial of our disturbing function with respect to epsilon, as given by this very first term here. The upshot of all of this is that this partial, dr d epsilon, can also be taken as dr d lambda, which takes care of those annoying time terms that are going to pop up here and there. We can also consider the case where M2 is much smaller than M1 and M3. This is sort of putting us back into the CR3BP regime, except in this case, we do not need to assume that M3 is on a circular orbit around M1. Rather, it is on a potentially elliptical, but still fixed orbit about M1, because M2 has very, very little effect on it being so small. We are going to select the orbital plane of M3 as our reference plane, which means that the inclination of the third body is automatically 0. And we're only interested in exploring the variations in the orbit of M2 to first order in eccentricity and inclination. That is, we are assuming that M2 is on a nearly circular and nearly zero inclination orbit, which again is a relatively good description for naturally occurring bodies in the solar system, most of which lie very close to the ecliptic plane. In this case, we can modify the Lagrange planetary equations to be first order in E and I. These should all be understood as being specifically for M2. So we've dropped the subscripts here, but these are explicitly investigating the modifications to M2's orbit. And we're also going to take advantage of the fact that we can average the disturbing function, the perturbing potential, before we apply the Lagrange planetary equations. So these R bar averages are the averaged part of R due to the external perturber only. We will make the modification to the A dot equation that we just discussed, taking the partial in epsilon to be equivalent to the partial in lambda. And then we get this set of expressions. The E dot expression is greatly simplified because in the case of small e, this √1 minus e squared term is approximately of order 1. And so we can get rid of this whole part, leaving only the partial in var pi. And the same applies for both the var pi dot and capital omega dot expressions. All factors of √1 minus e squared, here, here, and here, can be replaced with just 1. So we're going to take these simplified expressions and our average disturbing function, and we're going to study the rising secular terms and then resonant terms and see what we expect them to do to the long-term evolution of the orbit of M2.